Article 250.52 of the National Electrical Code, or NEC, states that a metallic water line can be used as a grounding electrode conductor, or GEC. However, this excludes its use for interconnecting parts of a grounding system unless it's an industrial or commercial application. This means a metallic water line can't be a GEC to connect the grounding electrode to a residential building's electrical system. The NEC doesn't explicitly address using building steel as a GEC for interconnecting parts of a grounding system. Article 250.50 of the NEC states that the GEC must be installed according to the requirements of Article 250.64. Article 250.64a requires the GEC to connect to the grounding electrode via a bonding jumper or another approved method. This means the GEC must connect directly to the grounding electrode. It can't connect to the grounding electrode through another conductor like building steel. Therefore, you cannot connect to the steel from your main panel and then connect from your steel to the incoming water line within 5 feet of its entrance to use it as an electrode. The NEC specifies requirements for grounding electrodes and grounding electrode conductors to ensure electrical safety. These requirements aim to provide a low impedance path for fault current to return to the source, which facilitates the operation of overcurrent protective devices like circuit breakers or fuses. This helps minimize the risk of electrical shock and fire hazards. Grounding electrodes are typically made of materials such as copper or concrete encased electrodes, also known as UFA grounds, and must meet certain size and installation depth requirements outlined in the NEC. Grounding electrode conductors are used to connect the grounding electrode to the electrical system. The NEC specifies the minimum size and type of conductor required for grounding electrode conductors, depending on the size of the service entrance conductors. The grounding electrode conductor must be securely connected to the grounding electrode and the electrical system using approved methods, such as bonding clamps or exothermic welding. Building steel is sometimes used as a grounding electrode in certain situations, particularly in large commercial or industrial buildings. However, its use as a grounding electrode must comply with specific requirements outlined in the NEC. The building steel must be electrically continuous and connected to the grounding system using approved methods. Additionally, the building steel must be supplemented with other grounding electrodes, such as ground rods or concrete encased electrodes, to ensure adequate grounding performance. Metallic water pipes are sometimes used as grounding electrodes, but their use is subject to certain restrictions. The NEC allows the use of metallic water pipes as grounding electrodes if they meet certain requirements, such as being in direct contact with the earth for at least 10 feet and having adequate electrical conductivity. However, metallic water pipes are often made of non-conductive materials, such as plastic, or may have insulating joints or coatings that prevent them from being used as effective grounding electrodes. In such cases, other grounding electrodes must be used to supplement the metallic water pipe. The NEC also specifies requirements for bonding various metal parts of a building's electrical system to ensure electrical continuity and minimize the risk of electrical shock. Bonding involves connecting metal parts, such as metal conduits, enclosures, and equipment frames together using bonding jumpers or conductors. This creates a low impedance path for fault current to flow back to the source, which helps trip over current protective devices and clear ground faults. The NEC requires that all metal parts of a building's electrical system that are likely to become energized be bonded together to form a complete and effective grounding system. This includes metal water pipes, gas pipes, and other metal piping systems that may be present in the building. Proper grounding and bonding are essential for electrical safety. By providing a low impedance path for fault current to flow back to the source, grounding and bonding help prevent electrical shock, minimize the risk of fire, and ensure the reliable operation of electrical equipment. It's important for all electrical work to be performed by qualified and licensed electricians who are familiar with the requirements of the NEC and local electrical codes. Electrical codes such as the NEC are regularly updated to reflect new technologies and safety standards. It's important for electrical professionals to stay up to date on the latest code requirements to ensure that their work complies with the most current safety standards. Failure to comply with electrical codes can result in fines, penalties, and even legal liability. In addition to following the requirements of the NEC, it's also important to consider local electrical codes and regulations. Local codes may have additional requirements or restrictions that are not covered by the NEC. It's important to consult with local electrical inspectors or code officials to ensure that all electrical work complies with both the NEC and local codes. Proper grounding and bonding are critical for protecting people and property from electrical hazards. By following the requirements of the NEC and local electrical codes, electricians can ensure that electrical systems are installed and maintained in a safe and reliable manner. The National Electrical Code, or NEC, is a comprehensive set of standards and guidelines for electrical installations in the United States. It's developed and published by the National Fire Protection Association, or NFPA, and is updated every 3 years to reflect new technologies and safety practices. The NEC covers a wide range of topics related to electrical safety, including wiring methods, overcurrent protection, grounding, bonding, and equipment installation. It's used by electricians, electrical inspectors, and other professionals in the electrical industry to ensure that electrical systems are installed and maintained in a safe and reliable manner. The NEC is divided into several chapters, each covering a specific aspect of electrical installations. Chapter 1 provides general requirements that apply to all electrical installations. Chapter 2 covers wiring and protection, including requirements for conductors, cables, raceways, and overcurrent protective devices. Chapter 3 covers wiring methods and materials, including requirements for different types of wiring, such as non-metallic sheath cable, armored cable, and conduit. Chapter 4 covers equipment for general use, including requirements for receptacles, switches, lighting fixtures, and appliances. Chapter 5 covers special occupancies such as hazardous locations, healthcare facilities, and places of assembly. Chapter 6 covers special equipment such as electric signs, elevators, and electric welders. Chapter 7 covers special conditions such as emergency systems, fire alarm systems, and communication systems. Chapter 8 covers communication systems such as telephone, cable television, and data communication systems. Chapter 9 contains tables and examples that are used to calculate conductor sizes, overcurrent protection, and other electrical parameters. The NEC is a complex and detailed document, and it's important for electricians and other electrical professionals to have a thorough understanding of its requirements. The NEC is not a law, but it's widely adopted by state and local governments as the basis for their electrical codes. This means that electrical installations must comply with the requirements of the NEC in order to be considered safe and code compliant. The NEC is constantly evolving to keep pace with new technologies and safety practices. The NFPA regularly issues revisions and updates to the NEC to address new hazards and improve electrical safety. It's important for electrical professionals to stay up to date on the latest changes to the NEC in order to ensure that their work complies with the most current safety standards. In addition to the NEC, there are also other standards and guidelines that may apply to electrical installations. These include standards developed by organizations such as the Institute of Electrical and Electronics Engineers, or IEE, and the American National Standards Institute, or ANSI. These standards may cover specific aspects of electrical design, installation, and testing, and they may be referenced in the NEC. It's important for electrical professionals to be familiar with all of the applicable standards and guidelines in order to ensure that their work meets the highest standards of safety and quality. Grounding and bonding are two of the most important concepts in electrical safety. Grounding is the process of connecting electrical equipment and systems to the earth, while bonding is a process of connecting metal parts of a building's electrical system together. The purpose of grounding is to provide a low impedance path for fault current to return to the source, which helps trip over current protective devices and clear ground faults. The purpose of bonding is to create a low impedance path for fault current to flow back to the source, which helps prevent electrical shock and minimize the risk of fire. Grounding and bonding are required by the NEC for all electrical installations. The NEC specifies the methods and materials that must be used for grounding and bonding, and it provides detailed requirements for different types of electrical systems and equipment. Failure to comply with the grounding and bonding requirements of the NEC can result in serious electrical hazards. Electrical shock can occur when a person comes into contact with an energized conductor or metal part that is not properly grounded. Ground faults can occur when a live wire comes into contact with a grounded metal part, such as a metal conduit or enclosure. Ground faults can cause electrical equipment to overheat and catch fire. Proper grounding and bonding are essential for preventing electrical shock and fire hazards. By providing a low impedance path for fault current to flow back to the source, grounding and bonding help ensure that overcurrent protective devices will trip quickly and clear ground faults. This helps minimize the risk of electrical shock and fire, and it helps protect electrical equipment from damage. Electrical safety is a shared responsibility. Electricians, electrical inspectors, and other electrical professionals all have a role to play in ensuring that electrical systems are installed and maintained in a safe and reliable manner. Homeowners and business owners also have a responsibility to maintain their electrical systems and to be aware of potential electrical hazards. By working together, we can create a safer electrical environment for everyone. The information provided is for general guidance only and should not be considered a substitute for professional electrical advice. Always consult with a qualified and licensed electrician before performing any electrical work.